We are going to be dealing with aqueous solutions when we're talking about our reactions inside of a living cell. And it's important to understand that water molecules, when they are in solution, they do not always hold together in the H2O form. So what that means is that they tend to fall apart. And when they do fall apart, they fall apart into basically a hydrogen ion, which we see right here, which is H+. And we also get one ion that we call a hydroxide ion, which is an OH-. Now, one water molecule will fall apart into one of each of these. Notice that one is positively charged and one's negatively charged, and opposite charges attract. So that means that this is also going to be a reversible reaction. So water molecules are going to constantly be falling apart into these two ions, and then they will also be reforming back into the classic H2O. If you have a bunch of water in a glass, some of the water will be together, some of the water will be apart. Now keep in mind as well that if you do have a water molecule that is polar, and water molecules are always polar, we have one end that's going to be a little bit negative, and then we have the hydrogen ends that are going to be a little bit positive due to that polar covalent bond. And if we have extra hydrogens floating around, they could get stuck on here to that negative oxygen end. So we can end up with what we call hydronium ions, which are H3O. Now, we're not going to talk a whole lot about hydronium ions in here. But what is going to be very important to us is going to be the concentration of the hydrogen ions that we have in solution, because those are going to ultimately determine what we call the pH of a solution. Now, in pure water, which we don't normally have, but if you do have pure water, one water molecule is falling apart into one hydrogen and one hydroxide ion. So in that case, we would expect to have equal amounts of the two. So if we were to draw this as kind of a balance here, you've probably all seen the teeter-totter balances before, we've got an equal amount of hydrogen ions and hydroxide ions. That would be pure water, or what we often call a neutral solution. Most of the time we don't have pure water. Now, what we call acids and bases are substances that disrupt this balance between the two. So in other words, if we add an acid or a base to a solution, then we now have the scale tipped in one direction or the other. So if we talk about the acids and the bases, an acid is going to be any substance that increases the hydrogen ion concentration such that now we're going to have extra of the hydrogen ions. So if you had, if we draw this, get us a blank screen here. Suppose that we have pure water. Pure water, we have equal concentrations of the hydrogens and the hydroxides. So I'm just going to draw equal concentrations of both of them on this slide. So at this point, we've got that nice balanced scale. Now, if we take a classic example of an acid, which is hydrochloric acid, or HCl. HCl, if you dump this into solution, it tends to fall apart into a hydrogen ion and then also a chlorine ion. So if I go and I dump some of that into my little container here, I'm going to dump it in, it's going to immediately fall apart into hydrogen and chlorine. If you now count up how many hydrogens you have compared to the hydroxides, you will see that our scale has now been tipped in this direction, such that we have extra hydrogens compared to the hydroxides that we have. And the more hydrochloric acid we dump in here, the more unbalanced we will become. So an acid is going to basically increase the hydrogen ion concentration such that we end up with this situation over here, where we are unbalanced. We've got too many hydrogens compared to the hydroxides that we have in solution. Now we do also have this little chlorine here in solution. That does not affect what we're talking about with the relationship between the hydrogens and the hydroxide ions. Okay, so here we're really looking at the relationship between the two, whether we've got an equal concentration of them or whether we have more hydrogen or more hydroxide, as we'll see in the next example. A base, in comparison, is going to be any substance that reduces the hydrogen ion concentration. So a base is essentially going to tip the scale in the opposite direction, and we have two ways that that one can actually operate. If you look here, we have one example with with ammonia right here. Ammonia has a very similar structure to a water molecule. We've got basically a nitrogen that's attached to 3 hydrogens. And we talked previously about the fact that oxygen and nitrogen were extremely electronegative. So in this case, you've got 3 single polar covalent bonds, which means all of those electrons are over here near the nitrogen. That makes the nitrogen end a little bit negative and the hydrogen's a little bit positive. What that means is that if you were to throw this into a glass of water where there's a lot of hydrogen ions floating around, those hydrogens are attracted to that negative oxygen end. So they do attach, and we end up with what we call NH4, which does happen to have a positive charge there. Now, if that happens, we are essentially removing some hydrogens from solution. Now, when we say removing hydrogens, the hydrogens are truly there still in the solution, but they're going to now be bound hydrogens. So if we look at this, if we draw our equal concentrations of both, if we throw some NH3 in here, so ammonia in here, suppose this hydrogen is going to make its way over here, it's going to attach, so we're going to change this to be NH4. This one's now attached over here. When we talk about that little balance, we're really talking about the free-floating, or in other words, the unbound hydrogens and hydroxides. So once this extra hydrogen was bound up, it does not factor into this equation or this balance anymore. So notice in this case, after we add the ammonia, we end up with extra hydroxides compared to the hydrogens that we have in solution. So one way that a base can operate is by actually taking the hydrogen ion concentration down, so they can decrease the hydrogen ion concentration. If they do that, then that is going to tilt the scale to be heavy on the hydroxide side. Another way that they can operate is, as we see this second base example, sodium hydroxide operates by increasing the hydroxide ion concentration. If the hydroxide ion concentration goes up, or if we add hydroxides to solution, then it will also tilt the scale in that direction. So sodium hydroxide tends to fall apart into a sodium ion and a hydroxide ion. This will increase the amount of hydroxides that we have in solution compared to the hydrogen ions. So what we want to keep in mind is that neutral solutions or pure water have equal concentrations of both the hydrogens and the hydroxides. If we add an acid is going to make us have extra hydrogens compared to the hydroxides. And if we're talking about a base is going to tip it in the other direction so that we've got extra of the hydroxides.